So supposing the sun suddenly collapsed to become a black hole, the Earth would A, leave the solar system in a straight line path, B, spiral into the black hole to our doom, or C, nothing would happen. Same old, same old. Well, let's vote. Who says A, Mr. Dewick? A, we'd suddenly leave the solar. No one. Who says, Mr. Dewick, it's a black hole? Obviously, we would spiral into our death. 1, 2, 3, 4, 5, 6, 7. Who says nothing would happen? 1, 2, 3. What holds the Earth in place around the sun? Yeah. Let's look at the gravitational field strength that the sun exerts on the Earth. Our equation for gravitational field strength, which is little g, I gave that, which when you plug in the universal gravitation equation, little m cancels, we said this. Okay? If the sun collapsed into a black hole, Aman, would big G change?
No.
Would the mass of the sun change?
No.
Would our distance from the sun change?
No.
So would the gravitational field strength that the Earth feels change?
No.
Now, what a black hole does is it's so dense that in its immediate vicinity, it changes the gravity well from something like, remember that I showed you the video of the spandex sheet as an illustration for space-time? It changes the gravity well from something like that to something where there's basically a vertical gravity well and nothing can get out, because to get out of there you'd have to go faster than light. But that's in its near vicinity. In fact, that's when you get past the event horizon. But way out there, black holes don't suck everything in. They have so much mass that typically stuff will orbit them. And if you're not on a stable orbit, if you are spiraling in and you do eventually pass the event horizon, Kenley, nothing's coming out. Okay? Find the notes okay? Okay. If you're wondering what it looked like, we got right to here. And the front page looked kind of like this. I forgot to check. Was anybody else away? I think just Nat. Dan is still away. Okay. Remember, we talked about kinetic energy before we did the black holes. I put a bit of a fear into you, letting you know that in 2029, a massive asteroid called Apophis will be coming past the size of a football stadium. It'll be ducking below our communication satellites. I think I told you we detected it in 2004 in December, on December 24th, which was the same day as the Indonesian tsunami that killed 250,000 people. So it never made the news. It will make the news in 2029 when all of you are, you told me 27?
Sure.
Is that what you said? It'll make the news then. And we said there was a small chance that it could come back in 2034 and hit us. Since then, we've got enough data. It's not going to hit us, so we're good. But nothing makes us special. There's no reason why asteroids can't. You probably recall 4 or 5 years ago, there was an asteroid, a meteor that exploded over Russia and did a fair bit of damage. And that wasn't that big a meteor. We're not that special. So we should be investing in deflection technology. Then we looked a little bit at black holes. We looked at escape velocity. We talked about spaghettification. And we paused here. Kenley, did you find it? Okay, I'll loan you one. Hey, Kenley, what does A want me to find? Keep reading. One more word. Gravitational field strength. Liam, gravitational field starts with an F. Is this what it's asking me to find? No. And I'm telling you this because I am going to ask you to find a gravitational field strength on your test. And every year, some kid does this, and I have to give them 0 marks because, oh, I asked you to find acceleration, and you may have found distance correctly, Not what I asked you to find, just because they begin with the same letter. So what's our symbol for gravitational field strength? Little g. And on your formula sheet, I just gave you this. Nat, see where it is? It's the third equation on the gravity section on your formula sheet, which you have out in front of you, yes? And the fact I've been telling, because you just got back, I've been saying, get both of them out, have the blue sheet open to the equations, have the yellow sheet flipped over to all of the data so that you don't have to flip over to find the mass of the Earth or all that stuff. Old trick. And then we said, because we're universal, we're going to put our universal gravity equation, big G, big M, little m, over r squared over little m. And this gives us little g. It's big G, big M, over r squared. The other reason I'm emphasizing that so much, the next unit after spring break is going to be electricity and electrostatics. And would you believe that electric field strength is force of electricity divided by charge? It mathematically is going to be really similar. All right, let's crunch the numbers. 6.67 times 10 to the negative 11. The mass of this is 7.2 times 10 to the 31. What's the mass of the sun? 10 to the what? This is 10 times, roughly 10 times bigger than the sun. Should work. And 9.6 times 10 to the 9th. Don't forget the squared. It's probably going to be bigger than 9.8 because black hole. You get 52.1. So not crazy, only about 5 Gs. You could probably, even if you weren't in free fall, deal with it for a while. You could is that right? Yeah. So you could probably fly a ship into that location. Flying out would increase the Gs. You might be pulling 8 or 9. Probably if we did something like, oh, well, instead of having you sit in benches, we'll have you floating in a tub of salt water or something like that. That would be a workaround that would cushion you enough that we could probably pull it off okay. Did you get the answer? Be honest. No. Bigger or smaller? What did you get on your calculator? Oh, I was going to say, check the squared. Is my most common mistake. And then, although this is an acceleration, you could write meters per second squared. I've told you I always write it as newtons per kilogram because that pops out. So this is roughly 5 times bigger than the Earth. What will the escape velocity be? Will it be 5 times bigger than Earth's escape velocity? Newsflash, no. How did we, and I'm going to remind you how to derive escape velocity. A bunch of you have told me that you've memorized it, which is fine, but we said we solve for escape velocity by using conservation of energy. But we said we wanted to escape by getting all the way to the edge of the universe. The fancy phrase was out to infinity. Erica, what was our potential energy out at infinity? That's why we could cross that out. And we wanted to do it so perfectly that we came to a stop right when we reached infinity. So it was our kinetic energy out at infinity. We had this weird situation where our initial plus initial equaled 0. Don't panic. We're going to be okay. We ended up with a half m v initial squared. In fact, that v is going to be v escape equals minus, plus negative big G, big M, little m over r. That equals 0. Nat, we then decided to plus the negative over to the other side to make a prettier equation. We got a half little m v squared equals positive big G, big M, little m over r. Is the escape velocity the same for a big spaceship or a little tiny CubeSat? Yep. And then we wanted to get the V by itself. Erica, how would I get the V by itself? Times both sides by? And then how to get rid of a squared? By the way, if you haven't figured it out yet, this is the unit that I did all that formula manipulation for last year. Because can you imagine if we were plugging numbers in and I couldn't bear it. We can rewrite these in our head. It's so much cleaner, and you see how everything fits together. Because you get a lovely equation. You get escape velocity is, I need more room, Mr. Duick. Escape velocity is 2 big G, big M over R square root. We noticed kind of a neat pattern. We said that that's escape velocity, that's orbital speed, escape speed, orbital speed, escape speed. What do you get? You know what? I think if I just backspace, I have most of these numbers on my calculator. I would just delete the squared. I would multiply it 2 times in the front. And if I square root that, should be good. See if you get a 1,249.9, that. 1, 3 zeros, a 2, a 4, and a 9. And some decimals. Yes? So I'll go 1.00 times 10 to the 1, 2, 3, 4, 5, 6. Does anybody remember what Earth's escape velocity was? Earth's was 11,200. Just for giggles, I'm going to divide this answer by 11,200. It's about not, even though the gravitational field is only 5 times stronger, escape velocity 90 times bigger. Okay? Space travel's tough. Did I go too fast? Is that okay, Kath? Have you got it all? Are you enjoying your lollipop? Okay. Ben, can you read to me C, please?
At what radius?
So we're going to solve for R. Keep going.
From the center of the black hole does the event horizon begin?
Okay. This is a fancy term. The event horizon, that's where, to get away from the black hole, instead of your escape velocity being this, your escape velocity has to be bigger than the speed of light. So what we're going to do is we're going to start out with the escape velocity equation. And we're just going to let v equal the speed of light. C. So I would write this. C equals the square root of 2 big G, big M over R. Ben, where is the R? On the bottom of a? And inside a? First thing I need to do is get rid of that square root. How do we get rid of a square root? Both sides. That's going to give me C squared equals 2 big G, big M over R. Where is the R? On the? Yeah. Oh, wait a minute. I'll multiply the R to the top, and I'll bring the C squared to the bottom. C is on your formula sheet at 3 times 10 to the 8th, which you might remember from the relativity unit last year, but it's somewhere on that table of constants, I'm sure. I think I gave you the speed of light, did I not? Yeah, it would be unlikely if I forgot that. It's a fundamental constant of the universe. So it's going to be 2 big G. What was M, Mr. Dewick? 7.2 times 10 to 31? All over 3 times 10 to the 8th squared. And so, remember how I opened the question, how I opened the class with the question of if the sun formed a black hole, what would happen to the Earth? Nothing, because we're outside of the event horizon. Our gravitational field wouldn't change. But if we were closer than the event horizon, then you're out of luck. The event horizon of this black hole, 6.67 times 10 to the negative 11 times 7.2 times 10 to the 31 divided by 3 times 10 to the 8th squared. Do you all get 106,720?
Yes.
Now, that also means, let's suppose this star was a normal star, a huge star, but it started to collapse and started to collapse under its own gravity. It started to collapse, and it started to collapse. As soon as it collapsed smaller than 106,270 meters of radius, that's when it would become or be classified as a black hole. Until then, it's something else, usually a neutron star, because those are really dense, but they're not dense enough to have formed a black hole. Divide by 1,000. This star would have to be basically less than 107 kilometers in radius. If I double that, less than 213 kilometers in diameter, this star would basically have to fit into the Fraser Valley if we start at Vancouver and go to Hope. I think that's around 215 or 220 kilometers. I think I showed you the video last day of how like the sun would have to be the size of a small city. The Earth would have to be compressed to the size of a marble or a peanut. So, suppose the sun began to collapse, maintaining its mass but decreasing its radius. At what radius will it become a black hole? This is the event horizon. It's also called the Schwarzschild radius, and that's named after the German physicist who wrote the first paper on it. Okay. Well, it's the same procedure. We start with escape velocity. We get the r by itself. And we let v be the speed of light. So let's crunch that for the sun. And I know we just derived that equation, but I thought since you'd all turned the page, it was good practice. Let's see what we get. R equals 2 big G. What's the mass of the sun? Hello. What's the mass of the sun? Anyone? It's on your sheet. 1.98 times 10 to the 30th divided by 3 times 10 to the 8th squared. Is yours the calculator page that has all the constants built in as well? Yeah. It probably has the speed of light. There's probably a C. Again, though, the way they have that set up, sometimes it's less work to actually type the constant than it is to find the constant and bring, because you get math, blah, blah, blah. For me, it'd be easier just to go 3, scientific notation 8. Let's see what we get. 2 times 6.67 times 10 to the negative 11 times 1.98 times 10 to the 30th divided by 3 times 10 to the 8th squared. You get 2,934 meters. 35. 2,930 meters. If I divide that by 1,000, 3 kilometers times 2 to make it a diameter if the sun was compressed so that it was roughly 6 kilometers apart, it would become a black hole. Now, how does that happen? We'll talk about that in just a second. I showed you the black hole comparison video already, I think. And did I do Neil deGrasse Tyson's Most Astounding Fact video already? We'll get to that one in a second, but first, pause.